All right, we are recording. We are live. Audio and video should be up and running. So welcome back to structural analysis. I can't believe it. We're in lecture 20, man. This semester, it's weird how time works these days. It either seems to go by really fast or it seems to go by slow or somewhere in between. I don't know. Let's talk about logistics. So exam is graded. Everybody in the class should have received a PDF report. The way that I grade the exams with us doing the class online, normally what I would do in class is I would, grade the exam and give it back to you. And so you'd have an exam and you'd see markups. And I can't really do that if it's online because there's no physical exam. So instead I send everybody this report that shows, if you had any deductions, what those deductions were and why. And I got a couple emails. I haven't had a chance to respond to all of them. For instance, I think it was maybe Mr. Bauer that had one. I promise I'll get to those by the end of business today. But not too many because, you all did great. The average on the exam was really high. I was really pleased with it. I've got more details on that on a video that I posted to Teams because I really want to jump in today to our next topic, which is deflections. We started talking about deflections before the exam before our last week, and so I want to pick up where we left off, and I really want to dig into deflection. So let's just jump right into it. So we did trusses, we did reactions, we did shear and moment diagrams, and so really the first sort of part of this class is all about what I would call force response. So you put loads on a structure. How does it respond in terms of its forces, its moments? And so, we look at the external forces that keep the structure in equilibrium. We look at the internal forces that keep the structure in equilibrium. We look at the distribution of those forces. So when we do a truss analysis, we're looking at the internal axial forces. When we do an analysis of a beam or a frame, we're looking at the internal shears and moments. And all that is about forces. And now I want to move on to talk about displacements, and talk about rotations, talk about deformations. And before I get into like the math of it, let's talk about why. Like, why do we care about deflections in structures? Like, why do we care how much a structure bends or displaces? I want to talk about the physical, the real life implications, and then I want to talk about the analytical implications. So why do we care about it in real life? Well, we care about deflections in real life because we don't want structures to deflect too much. Now, to be clear, you could have a structure that, let's say, fails a deflection limit and is still safe. Like there are differences between what we call strength limit states and service limit states. So, and you'll learn a lot about this if you take steel design or concrete design. In design philosophies, the strength limit states are, if you violate a strength limit state, the bridge is falling down, it's going to kill somebody. But if you violate a service limit state, it doesn't mean that the structure is going to fall down, but it means that it's not performing its intended function. So an example of that would be something like roof deflections or deflections of ceiling members. I'm sure that probably most of you in this class have been in a house or a building or any type of structure that has a plastered roof. So you have the ceiling and it's got a plastered ceiling. So you got the roof and there's plaster on the ceiling that have been used for your finish. Well, common deflection limits, such as like a very common deflection limit we use in structural engineering, is L over 360. So we take the length of the beam, we divide it by 360, and we say you can't deflect more than that. And it's like, well, where do you come up with that? Well, the idea is that if it deflects more than that, then you'll start to crack the plaster. Now, that doesn't mean that the beam's going to fall down and kill somebody, but it certainly the beam is not performing its intended function. We don't want the plaster to crack. And so there are some physical reasons why we want to understand deflections. You might have a bridge out there that's perfectly safe, but if it's deflected that much, you might not want to drive on it. Just because it's safe and it's got enough strength doesn't mean that it's satisfying the users. So those are the physical, the real life reasons why we care about deflections. Well, what about the analytical ones? Why do we care about the deflections from an analytical perspective? Well, the main reason that we care from an analytical perspective is, I'd say, because of indeterminate analysis. You can't perform analysis on an indeterminate structure without understanding the relationship between forces and deflections. So a very, very brief but simple example is if I have a simply supported beam, that's statically determinate. But if I throw another roller in there, that becomes an indeterminate structure. And we don't have the tools yet to analyze an indeterminate structure. But we can conduct a thought experiment. If I look at that additional roller, I say, what's the deflection at that roller? The deflection is 0. Okay, and so if you have a 3x3, your system of equations, sum of forces in the x direction, sum of forces in the y direction, sum of moments, that's 3 equations, 3 unknowns. If I throw another roller in there, that makes it indeterminate. But how do I solve that indeterminate structure? I can recognize that the deflection at that roller is 0. But I can't use that if I don't understand how to compute deflection. So hopefully that gives you an understanding as like why we're talking about this, because I always want to make sure that's clear. Now that's the why. Let's talk about the how. The way that we're going to compute deflections in here is we're going to use energy principles. So let's just recap. With energy principles, we have the law of conservation of energy. Energy cannot be created or destroyed. And in structural engineering systems, we focus on 2 sources. We have the external work done to the system, and then the stored strain energy. Now, if I had a structure with just a single member in that structure, I might say that the external work done is P delta over 2, and then the stored energy is the term F squared L over 2EA, and that just came from the area of that triangular graph. Now that's if I have a system with one member. If I have a system with multiple members, like a truss, then and it's subjected to one load, then the work is still P delta over 2, but then I have a bunch of members that I have to sum up the energy of all of them. Okay. Now, and that's how we solve deflections, is we say, the stored energy has to equal the external work done, and we solve for delta. That's good, great, grand, and wonderful, except there's a little bit of a problem, and that's with the definition of the work, the external work done. If I look at the external work done, the P delta over 2, I can only solve for the deflection where the load is applied. Like the work P delta over 2 is only where that load P is applied. So I can only find the deflection there if I use just these terms. And I also wouldn't be able to isolate a single deflection if I had a structure that had multiple loads on it. If I had a truss with 4 or 5 different loads on it, then there's all sorts of different works. The work due to this load, work due to that load, work due to this load. I can't isolate a single deflection. So it's kind of difficult to use what we call a principle of real work, using the real loads and the real displacements. So to handle this, what we do is we say, I'll tell you what, if I can only determine the displacement where a load is applied, and I want to find the displacement at a particular point, well, then dagnabbit, I'm going to put a load there. And so we place a load at the point of interest. And so now what we do is we have a structure with 2 sets of loads on it. So a single structure, but 2 separate analyses. I have one with the structure with the original loads, which I'm actually calling P2, and then P1 is the structure with just a single load applied where I'm trying to find the deflection. So if I have a structure and I wanted to find the deflection, right there, I'm going to put the load right there. And when I say the load, we'll talk about what that means here in a second. And this is where we left off last time. We had, our stored energy, which is the one here on the right, and then the external work done, the one here on the left. And so, I know this looked like an algebra mess, and, admittedly it kind of is. But what we did is we took this and we sort of broke it down into some components. And there were some observations that we can make from this. First off, if we look here on the right, we can treat the 2 loads separately. So we can treat the structure with the original loads on it, and we can treat the structure with just that single load on it. We can treat them separately because we're isolating each of these regions. We're saying that the total work done has to equal the total amount of stored energy. But I can break those into these pieces, and if I'm breaking it away, then each of those pieces have to equal one another. And what we're going to find is that the most useful term is this U component. The idea that the energy inside this rectangular region right here has to equal the energy inside this rectangular region right here. And we end up coming up with this formula, which is a really powerful formula. And it may not seem that it's so powerful, but it really is, because I can find the deflection due to this set of loads by using the results from analysis 1 and the results of analysis 2 separately. And on top of that, I can find the deflection due to that second set of loads when the structure is subjected to any amount of P1. It doesn't really matter what P1 is as long as I track that appropriately. And so you ask yourself, if I look at that equation and I'm trying to solve for delta 2, what's the easiest choice for the value of P1? And I'd argue that the easiest choice for P1 is 1, right? Because if I set P1, this term right here, if I set this term equal to 1, well, anything times 1 is itself, and I've solved for the deflection, and that's what I'm after, okay? And so with that, that leads to the method of virtual work. And that is the method that we're going to use to determine deflections in any structure at any point, okay? So let's just go through this. And I have a full-blown sort of worked out example here in the slides. In case for some reason that we don't have time to finish the one that we do in class, I wanted to provide you with everything that you would need to do this. And this method, the nice thing about it is it works for any structure. It works for any type of loading. It works for any deflection anywhere. And there's really not a lot to remember. It's pretty simple. So let's talk about this. What is the method of virtual work? The method of virtual work, and it's sometimes you'll hear engineers refer to it as the unit load method because of what we do. It's an energy-based approach that we can use to compute deflections in any structure subjected to any type of loading. So today what we're going to do is we're going to focus on truss deflections. And we're doing truss deflections because everything that we derived up until now, we derived assuming that we had axially loaded bars. So when we do bending, maybe the formulas are a little different, but the method is exactly the same. Now, I want to also make a note here. If you open your textbook actually has 2 different chapters on deflections. So when you open it, there's a chapter on energy methods and then a chapter on what's called geometric methods. And so let me kind of explain the difference. Geometric methods are, first off, they really only apply to beams and frames. And the reason why is beams and frames a little different is that beams and frames are governed by a specific differential equation. Specifically, the differential equation for beams and frames is that the second derivative of the deflection equals m over EI. So if anybody's wondering why they took differential equations, like why does it matter? This is a very real place where it matters, is describing the deflection of a beam. The thing about, and let me be clear, some of those methods do have advantages over some. Like for instance, the conjugate beam method does tend to work pretty well when you have a beam that's subjected to a lot of point loads. But the thing is, the thing about virtual work is that it works for everything. It works for any structure subjected to any loading, and you want to find the deflection anywhere. And because it's so universal, and because it's kind of easy to remember, that's the only method we're going to use in here because it's so versatile. And so in order to explain how the method works, I could show you formulas, I can show you equations. I have found that the easiest way to explain how the method works is to just show you an example. So let's take a look at this truss. Okay, now first off, before we go into this, if you look at this truss, you should recognize it because we did this truss in class. In fact, this was our very first truss analysis problem that we did in class. So we've solved this truss before. So when I start throwing the forces, like, oh, the forces are this, like you should be able to dig back your notes and see how we came up with this. Now, what I'm going to do for this truss is I want to determine the vertical deflection at B. Okay, so at B, I've got this 20 kip load. And what I'm saying is I propose when I take this truss and I put these loads on it, this truss deforms. How much does point B deform? How much does joint B deflect? So that's what we're going to try and figure out, the vertical deflection. Now, that's point 1. Point 2 is whenever you do a truss analysis, what you will find is that you need more information. See, when we did this problem in the past, all we were given was just where the joints were, where the members were, and the dimensions of the truss. That's it. Now look at it. I've got these like A equals 4 square inches and A equals 3 square inches, which, by the way, I think I have some typos on here because I think I meant for these members to have different sizes, but I'll that in a re-upload if I need. So we're gonna, I've got cross-sectional areas for each of these members. We're also gonna assume that each of the members are made of aluminum. And the reason why that matters is because I need the Young's modulus. I need the E value. So in order to do deflection problems, you need to understand something about the geometry characteristics and the material characteristics of the structure that you're analyzing. So, before, we didn't really care whether the truss was made out of steel or aluminum or popsicle sticks. It didn't matter because, the force equilibrium wasn't affected. But now the deflection characteristics will be affected by what the structure is actually made out of. Steel beams will deflect differently than concrete beams. So we're going to need to know those properties. Okay. First step to do is to solve the truss. Okay. So we're going to solve the truss, and we're going to determine the internal member forces in the truss. Now, we're going to denote these with a capital F. That'll be relevant here in a bit. And again, like if you're wondering, like, oh, where the heck did Dr. Mike come up with these loads? We did this problem before. Okay, we've done this problem previously in the semester, and so I've got this member has such and such kips and compression. This member has such and such kips and tension. We did this problem in the past. Okay, and so those are the real. We call those the real internal forces. Next thing that you do is, because the energy expressions allow you to deal with the forces separately, what you do is you take that structure. You take all the loads off of it, take them all off, and then we're going to just place a single load on it. Now, first off, where do we put that load? Well, we put that load where we're interested in determining deflection. So for this problem, if I was interested in determining the deflection at joint, let's say D, I'd put the load at D. If I was interested in determining the deflection at E, I'd put it at E. Right now, I'm interested in determining the deflection at joint B, so I put the load at B. Okay. Now, this is kind of like I'm teaching statics right now, so I'm thinking, how do you define a force? How do you define a vector? Well, it needs two things. It needs a magnitude and a direction. So what's the magnitude? Well, remember our energy expression. What's the easiest choice for a magnitude? Well, the easiest choice is 1. So we're going to set this equal to 1. Now, here's the thing. If you want to think of it as like 1 kip or 1 kilonewton, that's fine. It's really just 1, but if 1 kip makes it easier to visualize, that's fine. Okay, so I put it at joint B. Now, that's the magnitude. What about the direction? Okay, well, this is a vertical deflection that we're trying to determine. We're trying to determine the vertical deflection at B. So I need to right now make an assumption. I'm going to assume that joint B deflects downwards. So I take that load and I place it downward. Now it's the same philosophy with reactions. If I get a negative deflection, it does not mean I need to develop significant emotional distress. It just means I assumed it was deflecting downward, and I was wrong. It's deflecting upwards. So just make an assumption and make sure that you keep track of your assumption. Now, here's the thing. You're going to have to take this truss and solve it again. So you're going to have to determine the reactions, go through your method of joints and solve it again. And that I get it that could just suck. It's like, oh, I got to do it again. But it sort of is the nature of the beast. First off, because you're solving the truss again, it's not as bad. You've already figured out all the slope ratios and all the dimensions and all that. You've already got that figured out. Number two, if you have a structure subjected to like 15 loads, and now you're doing a completely separate analysis where it's only 1 load, remember what we talked about with zero force members? That is something that can definitely make your life a little easier. Also, another thing that can make your life easier is symmetry. If I look at this particular problem, if I put a joint load at B acting downward, that's a symmetric structure. So once I solve half of it, I'm done. I don't need to solve the rest of it. So if you can employ symmetry, or you can identify zero force members, it can make your life a lot easier as you move forward with the analysis. Okay. Before I move on to the actual computations, is everybody okay with just the idea so far? We do 2 separate structural analyses. We do the real forces that are present on the structure, and then we do this virtual analysis where we put a single unit load where we want to find the deflection and in the direction that we assume. Is everybody okay with that so far? And we denote those with a little f. So we did uppercase F for the real forces and a lowercase f for the virtual forces. And we call it a virtual so we call it a virtual structure and a real structure. Everybody with me so far? And my audio is coming through clearly, isn't it? I hope so. Okay. All right, good. All right. Okay. So now what happens is we have two sets of results. We have all of the capital F values. We call those the internal member forces from the real loads, and those are measured in kips usually. That's another thing. We're going to pretty much primarily deal in US units, really much metric here. And then we have our virtual forces, which are technically unitless. Now, we're seeing the same process. The internal energy is the little f, the big F, the L over the EA, and we just sum all those up. And again, that's just, if you go back to, let's say, slide 4, here's slide 4, and you look at this formula right here, this FFL over EA, and ask yourself, what am I doing? Well, it's just that. I'm just the FFLA, just summing that up for all the members. And then I'm saying that energy has to equal, P times delta. But remember, we chose a P value of 1, so it just equals delta. So it's pretty easy. Now, I do want to talk a little bit about the units, because that's a very easy mistake that you can make. What are the terms that goes into this fraction? Well, we have little f, which is unitless. We have big F, which is in kips. What about the E value? E values are moduli of elasticity. Those are your Young's modules, and that's usually in kips per square inch. A is your cross-sectional area, and those are square inches. And then L is the length of a member. Let me ask you a question. What should we express the length of the member in? Because normally when we look at a truss analysis, let's go back to our previous, slides. The truss, here's the truss, and the truss is in feet. That's 6 feet long, 8 feet long. So so convert all of your member lengths to inches. Okay, that's very important. Okay, now what I'm doing is I'm summing up this fraction for every member in the truss. And so when I'm applying the method of virtual work, typically what I'll do is set this up as a big table. Okay, and so I'll have 5 terms that I'm trying to report, and then a computation at the end. So the little f, the big F, the L, the E, the A. So notice how the length values are expressed in inches. And yeah, I have a typo, I think, on the slide, because I had meant for these values to be 3 and these values to be 4. So I'll fix that in the slides. My apologies for that. And so what I need to do is I need to record the little f values and the big F values. When I do that, typically what I do is I need to, I'm going to be doing computations and adding values up. I need to pick a sign convention. Currently, what we do is record the tensile forces as positive. There's nothing, actually with this part here, if you wanted to record compression as positive, that's fine. You just have to be consistent. Like if tension's positive, it's got to be tension positive across the board. If compression's positive, it's got to be compression positive across the board. Either one's fine. We typically just go with tension positive, just because tension tends to make members longer, tends to increase the length. That's why we go with tension positive. All right. And then row by row, if I've got little f, big F, L divided by EA, just compute that for every member. And so if you have a really, really big truss, you're having to do this a lot. So just a note here, Excel makes your life a little easier doing a lot of these computations. So for those of you in the class who are fans of Excel, this can make your life go a lot quicker. Now, when we do this and you look at all of your terms here, you get positive values. If all of your values turn out to be positive, what that means, I'm a big fan of Excel. Most engineers love Excel. If all of your values are positive, what that means is that when you assumed the deflection was downward, that means your assumption correct, that we assumed it was deflecting downward, and it in fact is. If you get any values that are negative, or if they're all negative, that means that your assumption was incorrect. Again, it just means your deflection is going in the opposite direction. You can get zero forces here, so don't let that freak you out. Especially if you have like zero force members in your structure, that's no big deal. And there is actually a very, very odd case where you can get positive and negative values, but the only time that ever happens is when the deflection is 0, and that is incredibly rare. So I would almost just say that that almost never happens in real life. And so the summary of the example, we have our structure, we determine the real forces, we determine the virtual forces, we computed all this out. We applied a downward virtual load, and we assume by assuming it was downward, when we got a positive answer, that means in fact it is deflecting downward. And the sum of all of these values, if you see here at the bottom of the table, was 0.237. So what does that mean? The deflection at point B is 0.237 inches going downward. And that is how we compute deflections in structures. If you understand that principle and that method, that's it. That's pretty much it. And it's the same method for beams and for frames. The method is the same. The only difference is the grunt work mechanics. In beams, we can't use just numerical sums. We have to integrate. But I mean, that shouldn't be all that surprising. I mean, remember, go back to Calc 1. What is an integral? It's a sum. All right, before we try and move into an example that we're going to do in person, like an actual in-class example, help me out. Are there any questions? Anything about this that's a little funky? Anything that's a little weird? That's my goal. That's my goal, is for this to be reasonable. I've taught this method, a number of years, and when you're like, okay, we got to do the structure twice, and we just put this one kip load magically wherever. It's like, what? I try and make it easier. All right, we're going to do this problem in class, and I want to try and I don't want to say skip some steps, but I'm going to try and go through it somewhat quickly because I want to get through it. And the problem with truss deflection problems is that they're not hard, but they can be long. So I have a truss. I want to determine the vertical deflection at joint C. Now, we're going to assume that each of these members have an E value of 29,000 KSI. But what that means is that they're made of steel. And so all the vertical and horizontal members have a cross-sectional area of 2 square inches, but the diagonal has an area of 1.5 square inches. So 5 members. Let's get right to it. All right. One of the first things I'm going to do before we actually start an example is I'm actually going to set up a quick Excel sheet on this. And maybe I'll cheat here a bit. I know. I don't know what to tell you. You're an engineer. You can't run away from it. All right. Okay, so here's the truss, and I'm doing this just to make some of the calculations that we do later a little bit more straightforward. So we're going to have our member, and let's just write out how many members we've got. So we've got member AB, we've got member AD, we've got member BC, we've got member BD, and we've got member CD. Okay, and what we're going to have is the little f value, which is unitless. We're going to have the big F value, which is in kips. We're going to have the length in inches. Remember, and I'm going to highlight that whenever you're doing this, the length needs to be in inches because, for your units to work out. We need E in KSI, and we need A in square inches. And I'm going to sort of move this over here. And then we're going to do little f, FL, EA in inches. And so maybe I'll make these columns a little bigger so we can kind of see what's going on. Okay. And so right off the bat, the first thing I'm going to do is see if I can fill in some of the values just right now. So we know that each member is made of steel. So we know this is 29,000 square inches. And as for the cross-sectional areas, we know that they're all 2, except for this one is 1.5. Because if you look at the truss, you can see that one's 1.5. Okay. Now let's do the member lengths. So the member lengths, we've got member AB is 6 feet, but that's 12 inches, or 12 inches per foot, so 72. Same thing with member CD. Member AD and BC are 8 foot long, so that's 96. And then BD is 100, yeah, so equals 10, or sorry, 120, I should say. Thank you. Now, I'm also, because this is Excel, I'm going to go ahead and set up this computation here in the column. So little f times big F times L divided by E times A. Drag that down. And then this value here is going to be my deflection, whatever that is. So the table's already set up. Oh. That's the table. That's that. And there we go. So everybody okay on setting this up? I mean, I don't think this is anything that's, too complicated. Here, I'll put that right there. So once we've got this set up and we just start putting our values in, we should be rocking and rolling. Let me shade it a bit. Okay. All right. Let's go back to the computations here. So now we got to just start doing our computations, and let's see what we can figure out. So our goal is to find the vertical deflection at C. Okay. So I propose what we're going to have to do is we're going to have to do 2 separate analyses. And so maybe what I'll do is draw a big vertical line and say I'll do one set of analyses on the left and another set of analyses on the right. And so we're going to have to do a completely separate structural analysis over here. Here's the structure. And, we've got, I can do better than that. We've got that. Got that. That. Now our goal is to determine, what is it, the vertical deflection at C. So somebody help me out. Take a look at these loads, and what do you think? Do you think C is going to deflect upwards or downwards? Remember, this is C right here. So make a guess. Is C going to deflect downwards or deflect upwards? Downwards. Okay. So we're going to put a single vertical load. And if you want to think of it as one kip, that's fine. Typically, I just try and think of it as one, just to differentiate it from the real structure. Okay. Now, first off, let's look at this real structure over here on the right. So let's see what we can figure out here. So this is the real analysis. All right. Now, can anybody look at this structure? So maybe we ought to do is say, oh, can I have a reaction here that's dy, probably going to be upwards. We got a dx reaction here, ax reaction there. So we'll call that ax, call this dx. Help me out. Anybody see any zero force members in this truss? We'll see if everybody sees that. By the way, I'll go ahead and say, you know, we've got a dy here. We're going to have an ax there, and sorry, a dx right here.
Could it be member AB?
Probably not AB, but you're close. If you look at joint A, I have if I look right here at joint A, I have a horizontal load. So this member is going to carry some load, but this one's not. The vertical member is going to be a zero force member, because there's no way that there could be vertical load on that joint. Likewise, and I believe Mr. Blizzard said this, that BC is also a zero force member. That's exactly right. Okay. And the reason it's a zero force member is because of the same thing. If I look at this joint right there, I've got a lateral load, right? Lateral load tells me that this member carries load and that vertical one's zero. In fact, you could also sort of look at this, make this a little easier. What is the force in member CD?
60 kips tension.
Exactly right. See, so this isn't so bad. Like you know, with some of these tools, you can knock this truss analysis pretty easy. In fact, this member is AX in compression. Whatever AX is, we haven't figured that out yet. Now, how about over here? This is joint B. This is joint C.
I have to ask.
Anybody see any zero force members we can isolate over here?
Why is BC really a zero force member? Because with the 80 kits pulling down on it,
Well, don't forget this. There's a diagonal member that can pick that up.
Yeah, I know that, but I thought it would be equal to, might balance out or something. But
not necessarily. It's a fair question. It's a fair question. And the reason I would say this, if we didn't have what was going on at joint C, I don't think we could definitively say it's a zero force member. But because of what's going on at joint C, I'm saying, yeah, it is. How about the virtual structure? How about the virtual analysis? Any zero force members you can identify? There you go. This is definitely a zero force member right there. That's correct. Any other zero force members? And on top of that, we know that this member is 1.0 in compression. And AD is zero force. Exactly right. So yeah, there's a lot that you can figure out. You can also say that this is going to be AX in compression. So you can figure a lot out without even like breaking out the pencil and paper and doing any structural analysis. In fact, let's take a look at the virtual analysis structure. In fact, take a look at this virtual structure. Take a look at the joint analysis on joint D. Those are zero force members, the horizontal and the vertical coming into to joint D. So I propose then that this is just dx squared plus dy squared. Now, can somebody help me out? Is that going to be tension or compression? What do you think? Tension, exactly right. Because if you look at joint D, you know, here's joint D. There's a member, and a member, and these are zero force, and you're going to have action there and a reaction there. You know, that's got to yank away. It's got to be in tension. So actually pretty slick. All right. Needs to point in the opposite direction of the two reactions. Exactly right. Okay. Let's stop. Let's see if we can do some number crunching here. So first off, let's see if we can do the support reactions. Let's start over here on the left, okay? So if I got 80 kips going down, if I sum forces in the y direction, if I got 80 kips going down, I got to have 80 kips going up. So that's got to be 80. All right. Now, as for the horizontal reactions, I know that they got to sum up to be, what, 60? But that doesn't really tell me much. Why don't I sum moments at one of my joints? Maybe I'll sum moments at D. So if I sum moments at D, think I don't have to consider dx, I don't have to consider dy, I don't even have to consider the 60 kips. That makes my life pretty easy. In fact, all I have to consider is the 80 kips times 6 feet, and then I got the ax at a moment arm of 8 feet. So ax is going to equal what? $80 times 6 equals what times 8? It's 60. 60 kips, and it goes that way. And so this right here, that's AX is 60 kips. And if AX is 60 kips going that way, if I sum forces in the X direction, somebody tell me what DX has got to be. $120 kips. There you go. 120 kips to the left. So 120 kips going that way. And so now we pretty much have this entire truss solved, except for one thing. We got to figure out that diagonal. And so I propose we do an analysis of joint D. And so if you do an analysis of joint, oh goodness. If you do an analysis of joint D, here's what you're going to find. You're going to find that, hold on, let's see. You've got, here's the joint. We've got a vertical member. Well, let me move this over so I'm not crunching here. All right. You got a vertical member, but we said that's a zero force member. You've got a horizontal member, but we had already figured out that that's 60 kips in tension. You've got a horizontal reaction that's 120 kips, and you've got a vertical reaction that's 80 kips. All right. And then we got this diagonal member. Well, I propose that has to be 80 kips going down. And what about the diagonal? What about the horizontal component? Well, I've got 120 to the left. I got 60 going to the right. I need another 60 going to the right. And on top of that, that member's at a 3-to-4 slope ratio. And 60 to 80 meets the requirements of a 3-to-4 slope ratio. So therefore, member BD is the square root of 60 kips squared plus 80 kips squared, or 100 kips in tension. Boom. I've got the entire truss solved. Okay, because look, there's 5 members. 2 of them are 0. The top horizontal is 60 kips in tension. The bottom horizontal is going to be 60 kips in compression. The diagonal is 100 kips in tension. And so now what I can do is I can say, well, if I've got that figured out, let's go to my table, let's report all that. So let's do just that. So go to my table here. All right, so we got our unit list values, and then we have our real forces in kips. And so let's just start writing that out. Now, member AB, that's the member on the bottom, and that was in compression. So we're going to say minus 60. Member AD, that's the vertical member right here. So that was 0. BC, that's this vertical member. We got 0. Member, what is this? Member BD, that's the 100 kips in tension. And then we've got 60 kips in tension right here. And there we go. Now we just chug out the same thing for the truss over here. And we've already got a lot of the members figured out. In fact, we have them all figured out. We have 2 of them are 0. We have a 1 kip in compression, this AX in compression on the bottom. The only thing we have to do is figure out our support reactions. That's actually pretty easy. So, all right, give me a second. So let's put some dimensions on here. This one was 6 feet. This dimension is 8 foot. So I propose if I sum forces in the y direction, if I have 1 going down, I got to have dy is 1 going up. So this is 1. And again, if I'm going too fast on the truss analysis, let me know. I'm trying to rush on this. So if you got any questions. Is compression always going to be treated as negative, or is that dependent on the axis we create? So it's not dependent on the axis we create, because let me answer 2 parts. So when it comes to compression, compression and tension are independent of which joint you look at, which direction you look at. That's why we express them as compression or tension. So it doesn't matter what way you look. As for, do we always consider compression to be negative? I would say that in this class we are. For you as an engineer, you can treat compression as positive if you would like in a virtual work analysis. You just need to be consistent. It either always needs to be positive or it always needs to be negative. I've always found it's easier just to treat tension as positive. And as long as you're consistent. All right. Let me see if I can knock out this truss real quick. I'm going to sum moments at D just like we did before. And so if I sum moments at D, I've got this single unit load at a distance of 6 feet. And that has to be counteracted by AX and a moment arm of 8 feet. And that's my how I'm going to solve for the reaction. So I propose then that AX is going to be 3/4 that way. Okay, it's going to be 3/4 that way. So it's not 3/4 of a kip; it's just 3/4. And if AX is 3/4 to the right, well, take a look at the structure. There are no forces going to the left or right on the virtual structure. Remember, we're analyzing this truss right here. This is the truss we're analyzing, and there are no loads to the left and the right other than reaction. So if AX is 3/4 to the right, DX is 3/4 to the left. Okay, so now I basically have this entire truss solved too, because I've got 2 zero force members. I've got AX in compression on the bottom, which is 3/4 in compression, so it's negative. I've got 1 in compression on vertical member BC, and then the diagonal DX plus DY squared in tension. So let's just plug that in. So AB, that's negative 3/4. We've got AD, we determined that was 0. BC, we determined that was 0. BC was -1. Sorry. BD, now that's the Pythagorean theorem, so square root of 3/4 squared plus 1 squared. And it's positive because that's a tension, so it's 1.250. And so that right there, that's your deflection. In fact, let me squunch that up a bit. Typically when we do deflections in structures, we don't do any more than like 3 decimal places because you're not going to be that accurate in measuring it in the field. So what is the answer? I propose then that the deflection at joint C in the y direction is 0.401 inches down. And that's the deflection. That's the answer. I know that was probably pretty quick, but again, this truss was really tiny. I wasn't trying to give one that was super super big. Any questions before we call it? I have a problem. I have a truss that I'm going to give you all as a homework assignment where you're going to do just a vertical displacement, but a horizontal displacement. They're at the same joint, so just like with the vertical displacement, with the horizontal, you're going to have to make an assumption as to whether or not you assume that that truss is deflecting or that joint is deflecting to the left or to the right. I see a question in the chat. How is AX and DX 3/4? It comes from wait. Oh, so the reason that AX is 3/4 is because of this right here. Okay. So if I sum moments at D, think about what happens if I sum moments at D. Look at the virtual structure. If I sum moments at D, I only have 1 times 6 from the vertical load at C, and then I have AX times 8 from the horizontal reaction there at the bottom. So, 1 times 6 has got to equal AX times 8. So that's how I get 3/4 for AX. As for DX, there are no, that comes from sum of forces in the X direction. I admit I did that a little fast. But if you sum forces in the X direction, the only thing you have is DX to the right, so you got to have AX to the left. Or you have AX to the right, so you got to have DX to the left. And if it's 3/4, it's 3/4. No, that's fair. I did that kind of quick. That's okay. That's okay. No problem at all. No problem at all. Any other questions? I know we got a couple folks logging out. I know y'all probably have classes coming out. All right, well, next week we take this and we do it for real because we start doing beam deflections. I'll derive the differential equation for beam deflections, and then we'll use it we'll use virtual work to do some really good stuff. But that's all I have, everybody. I will see you all next week. You all have a wonderful weekend. Yes, there is a homework this weekend. It will be due on Monday. It's a truss deflection homework assignment.